Once upon a time, back in the 1960s, I came across a book by the Norwegian author Andre Bjerke, New Contributions to Goethe's Color Theory. I did the prismatic experiment described therein and saw with excitement this variety of color spectra and their systematic relationships, which was all completely new to me. If you look through a triangular glass prism at this black figure, holding the prism horizontally, colors appear. Instead of the sharp boundaries between black and white, you get colorful borders. At the upper edge in yellow and red, at the lower edge cyan and blue-violet. These are the so-called boundary spectra. If we make the rectangle thinner, we force the red and the blue borders to meet and finally overlap, creating a new color called magenta or purple. The resulting spectrum in yellow, magenta and cyan is called the inverted spectrum. When the white areas completely meet, the spectrum fades out. Alternatively, look at this white rectangle on black ground. Again, you get the boundary spectra. If you make the figure thinner, this time the yellow and cyan borders will meet and create green. The resulting spectrum of essentially red, green and blue-violet is the ordinary spectrum. Observe that the spectra can be pairwise turned into each other by interchanging black and white in the picture you look at. A perfect symmetry. Light and dark play equivalent roles in the world of prismatic colors. It is evident that these four spectra together contain all hues needed for a full color circle. I spontaneously thought that I had to find out how this beautiful miniature color system might be analyzed and described in terms of physics. That turned out to be not altogether easy. I knew, of course, that color has something to do with the wavelength of light, but how to apply this knowledge to the phenomenon I now had before my eyes was not immediately given. I wanted to find out if Goethe had a point with his critical attitude against the Newtonian treatment of color, and why his own contribution was not regarded as relevant by the physicists of his time. Was there something essential Newton and his followers had overlooked? In order to find out the appropriate physical description of the prismatic color spectra and their systematic relationships, I preferred to consider what Goethe called the objektiven Versuche. In these, you send a flux of light through a prism instead of looking through it. If you place a prism on a white cardboard and let the sun shine onto the setup, it looks like this. Immediately behind the prism, there is a region of colorless light, which is, however, dispersed, which means light of various wavelengths within this flux have systematically slightly different directions. This is not seen until you place a shadow-casting object in the light. The tiny shadow behind the needle turns into a spectrum with yellow, purple and cyan. Alternatively, if you place a screen with a narrow opening in the flux of colorless light, a Newton spectrum in red, green and blue is obtained. At the boundaries of the light flux, you recognize the simple spectra, the yellow-red one and the cyan-violet one. Now I wanted to analyze the spectral compositions of the light at different positions in all of these various kinds of spectra. Starting with a simple boundary spectra, instead of doing it by theoretical analysis, using geometrical optics, I found a way to do it experimentally in a setup like this. By sliding screen S1 to various positions, you get on S2 a spectral analysis of the light at that position. Let us see how it looks. Here we go successively into the yellow boundary spectrum. You see how the full spectrum of light at first loses its violet end, then the green middle, until you are left with red and finally end up in darkness. Doing the same with the blue boundary spectrum, we cut away components from the long wave side, first to the red, then green, and we are left with the short wave violet. Summing up with diagrams, it looks as follows. To the left, you have the analysis of the yellow boundary spectrum. To the right, the blue one. Observe the symmetry. You seemingly cut up the full spectrum in two parts. They are complementary, in the sense that if you add them together, you get the full spectrum, representing white. So, cutting away more and more light from the shortwave side of the distribution, we generate a series of colors continuously running from yellow via orange to red. Cutting away light instead from the long wave side, we generate the series cyan, blue, violet. The secondary spectra, which include green and purple respectively, can be analyzed in the same way. They are the result of combining the procedures, either cutting away light from both sides, leaving a region in between, which in the limit ends up with light of a pure wavelength. Alternatively, analyzing the inverted spectrum, you see a dark region running through the spectrum. This dark region is thinner the farther away from the shadow-casting object you choose the point where you make your measurement. In the limit you end up with the full spectrum, in other words, just white. See the upper diagram. Obviously, when I speak of the ordinary and the inverted spectrum, this doesn't refer to specific spectra, but to two types of possible spectra. Which spectrum you actually get depends on the relative width of the strip in the middle. With a very thin dark strip on white ground, the overall impression may still be just white. With a very thin strip of light on a dark field, the resulting color will be very dark, even if highly saturated. For the illustration I have chosen an optimal width, making both the ordinary and the inverted spectrum come forth in full colors. For an understanding of the appearance of color in connection with the interplay of light, darkness and matter, we have to consider all four kinds of spectra and their spectral distributions. Together they supply material for a full color circle, as symbolized in the following diagram. I have now, by help of an analysis in terms of spectral composition, turned Goethe's colorful experimental demonstration into a set of diagrams. The formal relationships among these diagrams correspond to the qualitative relations we saw among the individual colors and color transitions of the spectral images. Taken together, these simple binary modifications of the full spectrum constitute a closed system of physically defined colors with interesting symmetry properties, such as complementarity, and with significant positions for the basic use in terms of brightness and darkness. What Goethe wanted to know was the objective physical grounds for the various color phenomena we observe in nature, and here he had a first clue to it. Of course, these binary spectral compositions are artifacts, and one may ask whether they are representative of colors met with in practical life. It turns out that yes, on the whole they are. For instance, an ordinary yellow surface may have a reflectance curve like this. Compare with the corresponding idealized reflectance. The natural distribution is smoothly varying, but the tendency is the same: strong absorption of light at the short wavelength side. Here is a series of yellow to orange color samples obtained from various concentrations of a yellow colorant. The cut-off wavelength is successively shifted towards the long wavelength side. Concurrently with the reddening, the sample by necessity gets darker, because more and more light is absorbed. It is in the nature of yellow to be bright and red to be dark. To arrive at the very red end of the tint series, you have to look through a thick layer of a concentrated solution, as here. So far, the use of the yellow boundary spectrum. But what about other regions of the color world? The following figure shows an example of reflectance spectra for strongly saturated color samples arranged into a color wheel. The physical color wheel is certainly not as perfectly symmetric as was the case with the ideal spectra. Well, this is how things look in practice. We are dealing with what Goethe called chemical colors. Two relatively broad absorption bands in various positions take us around the U-circle. Goethe was well aware of the fact that the idealized colors are highly artificial and searched for color phenomena in nature that could serve as concrete examples of the general scheme he had found. He decided on turbid media, displayed in the combined phenomenon of the blue sky and the reddening of the setting sun. These colors are not based on absorption, but on scattering, which is stronger at lower wavelengths, giving distributions like this, softly changing curves, but still compatible with the general scheme of ideal colors. So what have we learned concerning the physical correlate of color? A popular misunderstanding has been to relate U to the series of wavelengths displayed in an ordinary Newtonian spectrum. This goes back to a proposition in Newton's optics, where he suggested that every body reflects the rays of its own color more copiously than the rest, and from their excess and predominance in the reflected light has its color. Well, this might sound plausible, but as we have seen above, the reflectance of surface colors does not necessarily have a pronounced maximum at a position in the wavelength spectrum corresponding to its U. As a rule, it is rather the absorption of light in a certain wavelength region that determines the color, which means that the interplay of light and dark is decisive in the formation of color. Evidently, it is the distribution over the whole visible range of wavelengths that should be taken as a physical correlate of perceived color. We do not see selected simple rays of light, but we see the reflectance properties of object surfaces. Of course, Newton must have been aware of this. Consider the passage "more copiously than the rest" in the proposition above. Without this qualification, the statement would be meaningless. We have also seen that the reflectance curve of individual samples can show there were smaller variations within the total range. How to handle this fact? My idea is that what we perceive as color of an object has to do with whether the reflectance function as a whole is articulated towards the long wave side or the short wave side, respectively towards the center or the edges of the visible range of electromagnetic radiation, as suggested in the following set of diagrams. The eye doesn't perform a detailed spectral analysis, but it is capable of detecting a kind of second-order modulation of the light flux. The first-order modulation being the overall change in reflected light intensity, leading to more or less darkness of the sample. Conclusion. By applying a Newtonian analysis to Goethe's experimental observations, I have shown that there is no essential contradiction between the two pioneers' contributions to color theory. They rather complement each other. The series of elementary rays introduced by Newton can be used as a basis for defining and measuring spectral distributions. The way the initial distribution is modified when incident light is reflected from a surface or passes through a translucent medium is what determines the perceived color of the surface observed. André Bjerke, in his above-mentioned book, suggested that the reason why Newton avoided going into the nature of color experienced in practical life had to do with the fact that he performed his experiments in a dark chamber, whereas for Goethe, experimenting with illuminated black and white pictures, it was natural to regard colors as the result of modifications of colorless daylight. Furthermore, Newton's practical goal was to get rid of the colored borders that distorted the images in optical devices, but for Goethe, the intent was to understand colors we meet in practical life. I'm sure there lies something in Bjerke's observations, but still, there may have been a deeper reason behind Newton's avoidance of digging into the physics of color. After all, optics is the science of vision. How are we capable of perceiving something such as color? Like his forerunners, Newton held that colors must be understood as subjective sensations, caused by the action of the rays entering the eye. So he delegated the issue of color to the physiologists. That the quality of view is something subjective cannot be denied, but to see the world in color doesn't mean that what one sees is subjective. On the contrary, it conveys objective information about the world. What I see and how I see it are two different questions, and for me as a physicist, the first one had priority. But, to be sure, the second one is also intriguing. But that will be another story.
Thank you.